Greetings and welcome, friends. Mr. Waddy here. We're taking a look at section 5.4 from Algebra 1. Some of the homework problems on page 257. I did a sampling of them, trying to get some good ones here. It said, solve the system of linear equations. However, the name of this section was solving special systems of linear equations. And what made them special was the fact that they had the possibility of having no solution when, graphically speaking, they would have been parallel lines, or they could have had infinitely many solutions when the lines that the equations represent happen to be the same line, and so they intersect all over the place. When solving this, I could have used substitution, right? It's got some weak spots here and here, but I actually also noticed that it's got opposite x's, and oddly enough, it's got opposite y's. So I think this is already going to be in one of those situations where it's a special case. So step one is done, right? We've got opposite coefficients for one of our pairs of variables. Step two, add them up. Let's see, 3x and negative 3x is 0x, which is 0. Negative y plus y is 0y, which is 0, and 0 plus 0 is 0. I've got to at least write one of those zeros on this side of the equation. And 6 plus negative 6 is 0, and my variables all disappeared. However, because this is a true statement, I expect that this equation will have infinitely many solutions. Infinitely many solutions. Very good, very good. If my variables disappear and it ends up being a false statement, like 0 equals 2, then I would have no solutions, and the lines would have been parallel. So I'm expecting that graphically these would have been the same lines, and that's what would have occurred. Let's see, here's another problem. This one I also could do elimination method to solve, but hey, let's just do substitution, so I've got an example of each. So step one, I'll solve one of the equations for one of its variables. Elimination's probably quicker on this one, but like I said, I just kind of wanted to at least have both types of both methods show up. So x equals 2y plus 7. And if those two things are truly equal, which this equation claims they are, then I can substitute this expression in for x in the other equation. All right, so I'm going to plug that in for x. Now notice that's the opposite of x, so it's going to be the opposite of this entire expression. Make sure you use parentheses, like so. And then I could do some distributing, whoop, 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 whoop. And that's going to just opposite both of those. So that's negative 2y minus 7 plus 2y equals 7. And when I combine like terms, notice, oh dear, my y's, they cancel each other out, and I end up with negative 7 equals 7. Which is a false statement. Now, I would have had some similar false statement if I did solve by elimination method. I think I would have had 0 equals 14. Both of them which are false. And because it's false, therefore my conclusion is there is no solution to this system. These two equations have nothing in common with another. They were never going to find a point of intersection. All right. I liked this next type of problem where we were asked to use only slopes and y-intercepts of the graphs of the equations to determine whether the system has one, no, or infinitely many solutions. So the first thing I'm going to do is actually switch this second equation into slope-intercept form. So I'll subtract 12x from both sides, like so. So I'm putting it in y equals mx plus b. We just had a long weekend, internet friends, so you know, sometimes it takes a little bit for the math to come back to us. Let's see, to solve for y, we'll divide both sides by 2. Everybody gets divided by 2. Everybody. And I get y equals negative 6x minus 3. So between these two equations, let's analyze their slopes and their y-intercepts. So what is the slope of this first line? What are our thoughts? Y equals mx plus b. It's just the negative 6 for the slope. You could think of that as being negative 6 over 1 if you wanted, right? Or down 6 over 1, down 6 over 1. Just plain old negative 6. What's the slope of this line here? It's y equals mx plus b. The slope is the coefficient of the x, so it's negative 6 in this case. So they have the same slope, which means now we're in a situation where the lines are either going to be the same line or parallel. So what is the y-intercept, the b in this equation? Thoughts? Yeah, negative 2. Y equals mx plus b, and in this case, b is negative, so it's negative 2. And what's the y-intercept in this equation? That's the negative 3, right? So they're not the same line, but they had the same slope, so that means these lines are parallel, right? Parallel, and therefore there is no solution. All right, so that was done without solving and without graphing. That was just in my analysis of those, of their slopes and their y-intercepts. All right, last question. I've been moving a little bit fast through the other ones, but I like being able to do these. Take some time on this. All right, modeling with mathematics. So I'm going to write a system of equations that represents this situation, this real-world problem, so to speak, and then try to solve that system and see what the solution is. Okay, so it says a small bag of trail mix contains 3 cups of dried fruit and 4 cups of almonds. A large bag contains 4.5 cups of dried fruit and 6 cups of almonds. Write and solve a system of linear equations to find the price of 1 cup of dried fruit and 1 cup of almonds. So find the price, these are going to be our variables here. All right, the thing that they're asking us to do. So I'm going to say x is the price per cup of fruit, and let y equal the price per cup of almonds. Right? So I define my variables based on what the question is having me look for. Like 95% of the time, that's all you'd have to do to define your variables. Sometimes they might like ask a follow-up question. They might be like, do you like fruit? Or, something like random, and that's not going to be what my variable is. So look out for that. And as far as the price, what units should this be measured in? What are we paying for this in, probably? Well, over here, there's another fact. They were measuring those in dollars. So we'll measure ours in Americano dollars as well, right? Because they could have been in anything else. So let's write our equations. Now these are the hard parts. Okay. So I've got a fact about small bag, and I've got a fact about a large bag. I think that I'm going to end up having one equation that relates to things regarding the small bag. All right. And so this is what I'm thinking. And I know the price of a small bag. All right. So what is equal to $6? Well, that would be the number of cups of dried fruit multiplied by the price per cup, so 3 times x, and this would represent how much money I spent specifically on the cups of dried fruit in the small bag. And I'd add to that 4 cups of almonds multiplied by the price per cup of almonds, and so that's going to be y. And so this represents how much I spent on almonds in this entire bag. If I add those two quantities of price up, that would equal a total of $6. All right, so let's try to write another equation regarding the large bag. So a large bag contains, there's a fraction in it. And the large bag is equal to $9. So what equals $9? Well, the number of cups of dried fruit, so 4.5, multiplied by the price per cup, plus the number of cups of almonds, 6, multiplied by the price per cup of almonds, y. That's what I would end up having. So now I've got this system, and you guys are good at solving systems, right? The tough part is that writing these equations is usually the difficult part. I think what I'm going to do is I'm going to clear out the fractions in this. If I multiply this by the common denominator of all of those, well, I can, oh, the answer you're thinking ahead? Oh, I don't know. I don't know. I mean, well, I guess, like, yeah, it might not be an exact dollar amount. Yeah, maybe it's like $1.50 or something like that. So you're anticipating an answer already. But if I multiply this equation through by 2, the common denominator, right, because these denominators were 1, I can actually clear out all of the fractions. So let me show you this trick. So multiply by 2. 2 times 4.5. 2 times 4 is 8, plus 2 times a half is 1. That ends up being 9x. Plus, what's 2 times 6? 12y. And 2 times 9 is 18. And so all I did there, I'll just explain what I did there. I cleared out fractions. Yeah. Multiplying by the LCD, the least common denominator of all of the fractions. So that's what I ended up doing, right? So between 1, 1, and 2, 2 was the least common denominator, and so I multiply everybody by 2. All right. So now if I'm using this equation and this equation, let's get opposite coefficients. So for the x's, what is the least common multiple between 3 and 9? What's a number that both 3 and 9 could fit into? 9. Yeah. All right. And between 4y and 12y, what's the least common denominator between 4 and 12? Or, sorry, least common multiple is 12. So let's deal with the x's. Why not? So I'm going to multiply. Oh, actually, I usually write this in blue still, don't I? I think. What would I multiply this 3 by to make it 9? 3. And this one's a positive 9x down here. I don't want another positive 9. I need one of them to be negative so that they're opposite coefficients. In case you're wondering, we're solving by elimination method, right? There were no weak spots, so to speak, for the other ones. So let's see. Negative 3 times 3x is negative 9x. Negative 3 times 4y is minus 12y. Uh-oh. And negative 3 times 6 is negative 18. Oh, dear. So step 1, done. Step 2, what happens when I add these together? Everything became opposite. 9x and negative 9x is 0. 12y and negative 12y is 0. 0 plus 0 is 0. And 18 and negative 18 is 0. Well, but in the sense of infinitely many solutions, right? Because this is a true statement, there will be infinitely many. Let's see. Which is weird, right? I mean, what does that mean? Well, that means that I actually won't know the price per cup of fruit or almonds. That if almonds was more expensive, then fruit would have been less expensive. Fruit could have been more expensive and almonds could have been less expensive. But there's actually an infinite number of ways that could have happened and have these end up still being those prices per bag. So when I say infinitely many solutions, what I'm claiming is that there are infinitely many solutions that make this equation true. All right, that make 3x plus 4y equals 6 true. So it's not any combination of x and y. It's only the combinations of x and y that would land on that line. Let me just, I'll show you a quick graph. That is not writing. There we go. All right, so 3x plus 4y equals 6. 3x plus 4y equals 6. There we go. So here's the equation of that line. And just so you see what's going on here. So the solutions, there are infinitely many of them, but they are restricted. All right, they are only the ones on that line. And so let's consider a couple possible solutions. All right, so in our graph, let's see. X was the price for fruit, and Y was the price for almonds. So let's just consider a couple of these possible solutions. So I could have had, like this point would have been 50 cents per cup of fruit and $1 and, I don't know, what is that, 12 maybe, or $1.10, right, per cup of almonds. I could have also had this as a solution. I could have had $1.50 per cup of fruit. And what is that in almonds? That looks like that might be 40 cents per cup of almonds. All right, there's a possible combination. Now, this is technically a solution of the system, but probably doesn't make sense in real life, where fruit is $2 per cup and almonds are free. I'm assuming that's not the case, but theoretically, that could have been a possible solution. Similarly absurd but possible is, yeah, $0 for fruit and $1.50 per cup of almonds. Okay, so there's all sorts of possible combinations on this line, right? I mean, it could have even been, right, $1 per cup of fruit and looks like 75 cents per cup of almonds. So I don't know, but I do know a relationship between those prices, okay? And so that's, right, that's my answer, that the solution, right, the price per cup of fruit could have been any of them on that line. And maybe I'll write that down just to make it abundantly clear. So the answer, price for each could be any combination on the line shown. On the line. Right? So so that's kind of what we end up seeing. Perhaps you wanted to nail that down more. But actually, having this equation would be helpful if you happen to be the person who distributes and sells these bags of trail mix or whatever. Because if you want a consistent price for your customer, where you're charging, right, $6 for a bag of whatever, the small bag, you could see, right, if say suddenly there's a spike in price of almonds because of the drought in California and almond prices go up, you could say, hey, I need to try to like get my fruit prices down compared to what they used to be so that my customers will have the same predictable price, and then, you know, I'm not going to lose on sales. Otherwise, if almond prices go up and fruit prices stayed the same, right, then, you know, maybe you won't sell as many, but you got to figure it out. So like this line is meaningful in that sense, that you can at least kind of use it to make predictions or react to kind of market values. All right, thanks for watching, Internet friends.